Okay, good morning, good afternoon, good evening. I'm very happy to welcome everybody back to Thursday of week 2, multi-phase week. If you have been on our calls before, you know that we have now merged with technology, and we are using multiple platforms to engage with each other fully, and that includes simultaneously operating Slack and Zoom together in concert in beautiful harmony. So if you have not already, please do open up your Slack window, maybe on your phone while you're watching your computer screen. Maybe you've got 2 screens, 3 screens. Do it all, but make sure you join the channel, Halo 21 Week 2 Multiphase. Type your questions and comments in there, thread them so that we can monitor that channel while we're engaging in a rich discussion that will immediately follow the keynote presentation of today, which I will introduce in just a moment. And I just wanted to remind everybody especially who wasn't here on Tuesday when I gave the introduction, don't sleep on our beautiful Halo 21 new results videos. We have a YouTube channel specifically devoted to new results. One question came up recently, what is new actually? New is 2020 or later, okay? So if you have a paper that was published in 2020 that you want to advertise to our CGM community, you are absolutely encouraged to make a 4-minute video advertising your result. We have gone fully meta, so Cameron Hummel's uploaded a wonderful video on how to make a video. So if you have questions about that, you can go ahead and watch that video and then make your own video. So yeah, don't ignore the new results. They're getting rave reviews from everybody who watches them. So be prepared to have your mind blown. Okay, and then finally, I'm very happy to introduce today's speaker, Dr. Drummond Fielding, who will speak for the next 50 minutes or so. As soon as I'm done, we'll take a 5-minute break after that, where you can furiously type your questions and comments into the Slack channel, Halo 21 Week 2 Multiphase. And we will then have a panel guiding our discussion, where I will kind of moderate by monitoring the Slack, feeding some of the most interesting upvoted questions that happen on that Slack channel to Dr. Max Gronke, Dr. Evan Schneider, Dr. Prateek Sharma, and Dr. Jonathan Stern, all of whom will have great insight into the question of the week. Okay, everybody, it's 9:06. Welcome back. I see our expert panelists here, in particular, Evan Schneider. Hi, Evan, if you want to wave, go ahead and wave. It's Evan.
Hey.
Okay. And then we have Jonathan Stern, who actually just stepped away from his computer, so he can't wave right now. And Max Gronke, if you want to wave. Hi, Max. And Prateek Sharma, is he here? And Prateek, there he is. Hi, Prateek, thanks for waving. There's Jonathan. Jonathan, if you want to wave for people so they know you're one of our expert panelists. All right, well, that's Jonathan. Doesn't have his headphones in yet, putting his headphones in. Hi, Jonathan. Welcome back to the expert panel discussion. Okay, so there's a ton of really interesting questions and comments from the Slack based on what was being widely hailed as a tour de force classic presentation. So thanks, Drummond. That's exactly the kind of keynote we were hoping for. And in particular, what I really liked is that it juxtaposed, so I thought Todd did an excellent job on Tuesday of really, giving us an idea of how rich the data we have are, but also that they are limited to some degree as well in terms of what we can glean from them. And then you went ahead and showed us all of these beautiful predictions that really tell us of this interdependence of the different physical scales and processes happening that can distinguish, between the different phases that emerge in the CGM. And so I guess the first question I think would be a really interesting one for the panelists to address would just be, what are the properties that you most need? One of the things that I noticed, it looks like cloud sizes or stream thicknesses or masses or densities or metallicities or pressures. What are the most important constraints that observers should really focus on pinning down?
Yeah, excellent question. Since I just talked so much, do any of the panelists immediately want to jump in and chime in on that? Okay, well, I'll start. I kind of wanted to show that that little candy stripe visualization at the end there as as a hint towards what we might need. I do think it's very challenging because as you saw, a lot of these timescales were indeed relative to a cloud size, which is probably not something we're going to be able to measure so well. If we can get a robust observational probe of an individual cloud size, that would be, amazing. But I think we can learn a lot about the phase structure and the interconnectedness of the different phases in the clouds and the dominant processes by really looking at the line ratios and resolving the different lines like we were seeing in that multi-phase movie there at the end. So I don't know, I'm a little brain dead from all that talking, so someone else, I'll think of more things to that as we go.
Okay, I see Evan's unmuted.
Yeah. I was going to say, I could add something, I think, maybe just because I agree that cloud sizes are important. Obviously, that was part of the reason I derailed Tuesday with my question about what observers even mean when they say a mist versus a cloud. But I think something maybe we could get a handle on that is important to this whole discussion is sort of the actual spatial correlation of these different phases. So, Drummond's swipe viz, as I'm sure it will be known forever, does a really nice job highlighting that at least for some of these multi-phase models, the oxygen 6 should be very spatially correlated with these lower ions. And I think even in, some of the absorption line data, some of the really nice data, for example, that Gwen was showing, it seems like observers are starting to get a handle on that. And I think that not all of the sources of multi-phase gas that Drummond outlined will be as spatially correlated as that. So I think that's one area where it would be really helpful in distinguishing between some of these different models and some of these different sources of multi-phase gas.
I see Chris McKee has his hand up. Chris, if you want to unmute.
Sure. Can you hear me?
Yes.
Yeah. So I wanted to ask.
Oh, you just muted, Chris.
I just muted you. I meant to lower your hand. I muted you, Chris. If you want to unmute yourself now, I can't unmute you.
Okay. I'm unmuted now?
Yeah.
Yep.
Okay. Thank you. This may be, as I said, a question for the observers to try to get to the point that Drummond was making about cloud size. What are the prospects, particularly with the upcoming ELTs, to actually be able to get absorption line, spatially resolved absorption line observations? That is, instead of using a quasar, which is a point source, you would actually use a distributed source. And will there be the sensitivity and resolution to be able to do that with future instruments?
Well, we have our other keynote speaker with his hand raised, Todd Tripp, who has possibly thought about this question that you pose.
I just want to remind everyone about the excellent paper that Michael Rauch wrote many years ago, looking at gravitationally lensed quasars or just adjacent quasars, which placed some very interesting constraints on the sizes of the absorbers. And I think with future large telescopes, that kind of experiment could be revisited with larger samples and maybe even other species. I think Michael just looked at, well, he looked at carbon 4 and H1. I don't remember if there was a magnesium 2 paper, but that's a promising way with big ground-based telescopes to get some information on sizes.
And also those.
Following up on Chris's question, I just want to add one thing. There was some very nice work by Kate Rubin using background galaxies as the absorption source to sort of be able to constrain the size of the absorber, because the background galaxy is no longer a point source, it's resolved. And you could imagine, you know, that taking to the nth degree with even more powerful telescopes and really actually like looking at how absorption changes across the face of galaxy. That might be an incredibly powerful way going forward to really get at Chris's question of the spatial structure and the cloud size of these systems.
Okay, I see we have a lot of hands up. I'm going to ask, okay, what I'm going to do is, Gwen had her hand up before, so I'll ask Gwen to say something. And then I want to give a chance to all of the panelists to kind of, you know, give their view, their expert view. And then we'll go back to the kind of hand raising stuff. Okay, so Gwen, go ahead.
Yeah, so I just wanted to comment on this idea of using the ELTs to map the CGM in sort of a spatially resolved way. So as was just mentioned, if you use something like a gravitationally lensed background galaxy, you can actually sort of have a light table type situation. And then your resolution is basically limited by the resolution of the integral field unit that you're using, the spatial resolution. I think in some sense, our best hope is still going to be quasars, just because the size scale that they probe is limited by the actual, you know, the light from the quasar itself, which is small on at the location of these absorbers, whereas background galaxies are always extended, of course, and because of that, if the size scale of the clouds are much smaller than the projected size of the galaxy at that redshift, which will essentially always be the case, it appears, then what you actually measure is the covering fraction of this gas, as opposed to directly measuring its sort of size scale. And so I still think actually looking at larger samples of lensed quasars might actually be the path to this. There's also been beautiful work doing very, very careful photoionization analysis to try and get at cloud sizes. And we're at the point now when you do this sort of component by component analysis, where you see similar answers coming from that as you see from lens work, like Michael Rauch's work that's been pointed out, and then a paper that I published last year also showed a similar example in the CGM specifically. And so I think, you know, I agree that these sizes are really critical, and it's something that I think we really need to be paying close attention to in terms of trying to do any sort of comparison between simulations and observations. But I think in terms, like, you know, I'm super excited about doing these spatially resolved CGM maps using background galaxies. This is one of the main science cases for the ELT, but it's not, I don't think it's going to be crazy useful for measuring sizes. I think it's going to be much more useful for looking at the spatial correlation across the halo of structures and seeing whether you see large dramatic patterns in that structure.
Okay,
that's my guess.
Thanks, Gwen. Okay, I want to give each of the panelists time to kind of process some of this on this subject, or maybe they want to veer onto another subject that really inspired them from Drummond's slides. And I also just want to point out that some of these questions about sizes can be answered by looking at the Milky Way and being able to do kind of halo tomography. And so that's coming up week 4, and I'm sure we'll hear more about that then too, to plug week 4. Okay, so panelists. Who of the panel, it looks like Prateek has his hand up, he's on the panel, so you might as well go ahead.
Right. So I just wanted to add to this that I heard a talk by Celine Peru in ESO, and she was actually talking about extended galaxies mapping the foreground CGM. So it's similar to what Drummond mentioned. So it looks like, and also other speakers. So I just wanted to add that because I had heard that word. I think, yeah.
Thank you. All right, well, let's see. Max, what do you
Yeah, I mean, first of all, I want to thank Drummond for an awesome talk, always rock star-like, of course, and then congratulations. I mean, that's amazing news you shared with all of us. But for the science, I mean, I also wanted to mention Celine's work and also Sebastian Lopez, who uses lensed background arcs. I think that's very nice. But I think Joe pointed this out, you know, in the Slack channel. I mean, it's pretty clear, right, that the size is small. I mean, you know, the question is just how small, and I mean, seems to crystallize out, and that it's probably smaller than what we can do directly in observations, except maybe Milky Way. So I'm very excited about that week as well. And I just want to bring up one point that came up in the Slack discussion in the past few days, and has to do with that. That is that we have to be careful to correlate like sizes and sizes in velocity space, right? If you look at Kate Rubin's work, for instance, that was mentioned before, that's sizes in velocity space, so to speak. And so the question is, is because what Drummond showed essentially, right, is that there's these observations that show stuff that's very small, but then in order to make gas survive, it has to be somewhat large. So I think that that's some kind of interesting discrepancy, and I mean maybe somebody can say something about that.
Jonathan, do you want to add to that?
Yeah, two quick points. Can you hear me? Yeah, good. Yeah. Okay. So first, about the question about kind of what I think would be useful to kind of distinguish these mechanisms in terms of observations. One thing which I think is super useful is kind of gaining speed in the last few years is kind of mapping large-scale structure of the CGM. So kind of understanding, is the cool gas in the disk plane? Is it along the minor axis? I think these kinds of observations, which we kind of need lots of statistics, all these next generation of observers, is very revealing, right? Because once you know the location of the cool gas, right, that already kind of narrows down which mechanisms could create it. So it tells you a lot about that. If you know that the cool gas is not volume filling, like in a Kaprak showing that there's a bimodal distribution of cool gas as a function of angle from the minor axis, that also kind of narrows down which mechanisms, because that tells you that whatever mechanism is creating cool gas is not happening in the entire halo, it's only happening at specific places in the halo. So I think those kinds of observations, which are becoming more and more available, are becoming will be very useful in kind of to understand where we are on this wheel of fortune that Drummond showed. That's one thing. One more, kind of to add one more thing, cause of cool gas is rotation. Okay, when you go small scale, the hot gas is expected to actually rotate. That's another mechanism which would create a cool gas, and there's a few very interesting studies about that. So just to make that picture even a bit more complicated. Yeah, so I just wanted to mention that.
Great, and something that I just saw come up on the Slack that maybe somebody wants to weigh in, maybe Evan even is the person to weigh in on this, but so Crystal asked, and I think that this really gets to the crux of it. So how is size even defined for one of the simulation, like those kinds of simulations that we're seeing, right? There's little cloudlets with a distribution of sizes, and they're organized into larger scale coherent structures, right? So how do you actually, on a simulation, say now you have all the data on the simulation, how do you define it? So Evan, I'm going to let you go since you're on the panel, and then I'll take some hands.
Thanks. Yeah, no, I would love to weigh in on this because I think this is a question that I think we've gotten a little bit, I don't want to say distracted because I think these questions are theoretically very interesting, but a little bit distracted by the sort of minimum size of the cloud that we think should exist. But something that has struck me, at least in the vast majority of the theoretical work I've looked at, you can look at, for example, the potato cloud, shattering versus not shattering case from Max's paper that Drummond showed, is that even in the case where you shatter and you have many, many tiny little clouds, there's always large scale clouds as well. And so it's not clear to me, from the observations that those two cases would look any different, right? Especially if all you have is an absorption line. And so I think that this is an important question for us to sort of address theoretically is, we kind of, I think, agree that in our simulations, we're almost always getting some structure down to the resolution scale of the simulation. But is that the structure that matters? And we talked about this a little bit in one of the channels, and I've already forgotten which one, but Drummond alluded to it in his talk too, where it's sort of like, well, I think it depends on the question that you're trying to answer. the question you're trying to answer is, how much cool gas is there in the CGM? Maybe you don't really care if some of it is in tiny clouds, if that's not, the picture that we should have in our heads. And so far from theory, I haven't seen any simulations that indicate to me that the picture I should have is an actual, volume filling mist. I almost always see these larger scale structures. So I think that is an important point to think about, and whether or not observationally we would be able to distinguish between those two cases.
Well, and that gets me thinking too. It's like, so what you said, what's the question that we're trying to answer, right? For me, I think about where did the gas come from and where is it going, right? And so this gets to something that Xiaowen said, is just like, is there a way with some of these parameters that we can determine, cloud sizes, masses, to actually distinguish between the different origin scenarios or fate scenarios? Okay, so unless, and so, okay, maybe that just gets dangled. I said I would go to questions. I've seen Nir with his hand up for a while.
Hi, thanks very much. And also thanks to Drummond again for a great talk, and congratulations on the wonderful news. This might be kind of slightly a separate issue, but we've talked a lot about the formation of the multiphase gas kind of down to 10 to the 4. What do people think about the molecular gas content of the CGM? Is it at all possible to form that due to in situ thermal condensation or instabilities, or does a molecular gas necessarily originate in either an inflow or an outflow or ram pressure stripped, galaxy? Do we think it can form in inflows? Yeah.
Panelists, John.
So in principle, So I think in principle, if you're dense enough to self-shield from the UV background, right, then you can cool to very low temperatures and then create molecular gas. So I think that the densities are relatively low at low redshift, so it's unlikely. But perhaps if you go to a high redshift, redshift of 3 or 4, densities become much larger, self-shielding becomes much more important, then it seems reasonable that maybe you even reach the point that you get to molecules.
Mm-hmm. From thermal condensation in the hot CGM, or are you talking about in inflowing streams, or both?
If you manage to reach 10 to the 4K, whatever process you choose,
yeah,
okay, but you're dense enough to be self-shielded, then you will further cool.
So I guess the question is, do we expect precipitated clouds to be able to become dense enough to self-shield?
Yes, and that's expected at higher redshifts, where the densities are generally higher. Yeah.
Well, I don't know, because if the densities are higher, their sizes will be smaller, presumably, given the cooling length argument, right? So do we expect them to have a column density that would allow them to self-shield?
Yes, so it's actually, right, so what you care about is kind of what's the characteristic column density, right? So the density is increasing as 1 to 1 plus z to the third, and the sizes, right, are only decreasing as 1 plus z to the minus 1, right? So in the columns in the CGM are much larger at higher redshifts.
Right, okay.
Right.
Thanks.
All right, I said I was going to go to hands.
Wait, sorry, really quickly. Mark added a great point. You most likely need dust to form molecules. And so I know Max and Ryan Farber are working on the cloud crushing problem with dust and seeing how it can survive. So if you've just got sort of like a dust-free hot CGM with some perturbations and it's collapsing, even if it self-shields, I don't know if you're going to form molecules. So that's an additional point to consider.
Thank you. Yes, dust is the main way that molecules form in the first place. So it's good to remember that. Okay, so I have lost track of the time. I think I saw Marcus's hand a long time ago. So Marcus is trying to add something. Go ahead, Marcus.
Okay, well, maybe just want to make 2 points. I started writing on the Slack as well. I liked Drummond's Wheel of Fortune chart, and I think there's a bit of analogy, just like with equilibrium dynamics. Cooling is trying to pull the gas away to a new point of equilibrium, and all the other points, Kelvin Hamills, mixing, free fall, whatever you want, try to counteract this. And there's maybe 2 points one can make. One of these other competing processes is thermal conduction, and sometimes thermal conduction doesn't actually work the way it is. So you think thermal conduction would act against it, but I've shown in simulations with Evans Galapego that conduction actually, because it causes evaporative winds on the surface of these clouds, makes it actually compresses the cold clouds and makes them actually cool faster. So sometimes things are a little unexpected, even with these competing processes there. So that's not easy. The other thing that can complicate things, if you've got another phase in there, like cosmic rays or magnetic fields that talk to the gas, and they've got different state variables and different dynamics and different equilibria that they like to seek. And if they now communicate with the gas, then all hands are off. Anything can happen then. And some simulations have shown this, that if you've got other phases talking to the thermal gas, things become much more complicated. Maybe it's the bleeding obvious, but anyway, please discuss.
Those are really excellent points. Thank you, Marcus. The equilibrium dynamics is definitely a useful way to think about this. And as far as conduction goes, I'll just say for my own sake, Chris McKee, who I'm happy to see is on the line, was the first person I worked with in graduate school. The first paper I wrote was with Chris. And so I feel like I was raised on some of this stuff in a sense, like lately in particular, Greg Bryan and I have been looking over Cowie and McKee and Cowie 1977 and 78 to really, understand exactly these points you're saying: conductive evaporation, conductive condensation, and really trying to fold this into our understanding. I would say that, at least from the turbulent mixing layer perspective, I would say, Mark just said props to Chris McKee in the chat. I mean, yeah, exactly. I keep on thinking I discover something, and then it turns out Chris wrote a paper on it 50 years ago.
Yes,
yes, I think that's a statement of being a good theorist. Is that Chris has already done it. It's like The Simpsons did it. The point I was just going to say about the turbulent mixing with conduction included is, if this sort of effective turbulent conductivity swamps the actual thermal conductivity, then the overall evolution doesn't seem to look that different based on experiments I've done in work that Brent Tan published last year. And once they start to become comparable, I think that's a really important question. And as you say, add magnetic fields or non-thermal pressure, and it just gets more exciting. So I'm sure some of the other panelists probably want to add to that.
Yeah, looks like Prateek, you're a panelist. You don't have to raise your hand, Prateek, as a panelist. Right.
So I had a comment about molecular gas. In galaxy clusters, cores of galaxy clusters, most of the mass is in the molecular phase and not in the atomic H-alpha phase. And I think one of the very important reasons for that is also the pressure. If you look at the two-phase models, there again, Chris is one of the pioneers, Wolfire et al. Type models. The pressure plays a very, very important role in determining which phase does the cooler, do you have two phases coexisting, or is it the dense molecular phase or the less dense atomic phase? So I think pressure, in addition to dust and self-shielding, these are all very, very important. And pressure, I think, is, like galactic high velocity clouds do not really show evidence for molecular gas generally, but cluster filaments are very molecular. So, and the big difference between clusters and Milky Way halo is the pressure, I think.
Yeah, that's an excellent point. Very quickly, I just started a thread in the Slack channel because this is something that Greg and Shmuel and I have been talking about exactly this point, pressure being key. Sorry, Evan, go for it.
Oh, no, I was just going to use panelists' privilege and tag on to that this is related to a question that I saw in the Slack that I get a lot about whether or not these cooled clouds are going to become self-gravitating, because people want to know about star formation. I mean, it depends 100% on the pressure and whether or not you can actually cool down to the molecular phase. So in the average, Milky Way halo, no, you're not going to precipitate out cool clouds that are going to become self-gravitating. But in more, in higher pressure environments, I don't know.
Calling Stephanie Tonneson, who's been thinking about this in the intercluster medium in that simulation I showed. So she doesn't have to necessarily respond now, but good person to talk to about that if you're interested.
Okay, I want to get to something on the Slack channel, but I've seen Yuan Lee with her hand up for a while, so I'm going to ask Yuan to ask her a question.
Yeah, I think I had a question earlier, but now I want to follow up on what Mark mentioned about dust. And mostly, I guess my question is for the observers. I really don't know if we've observed dust in the CGM, either in the cooler phase or the warmer phase, hotter phase, whatever you call that. So what's the current status on observations of dust in the CGM?
There was a really cool result back in, gosh, I don't remember the year anymore, but Brice Menard and maybe Guangzhou Zhu, they found this like really cool like dust correlation in the CGM. And I've always thought about that. Like they see dust out to 50 kiloparsecs. It's a stacking experiment with SDSS data and using like extinction. And it's amazing. And so I will point out too, my own result as far as dust in the CGM in the Milky Way, we think probably that ionized gas can also be dusty. Chris Hauk did work on this, that in the WIM at least, the warm ionized medium that's kind of puffy, maybe, that there's probably some dust there too. There's evidence at least that there's significant amounts of dust there. I don't know about others.
There's been a lot more progress on the halo dust that calls into question the result by Menard. And it was by Johnson, I think within a year or two after that. And Hodges-Cluck has seen dust scattering, UV scattering by dust as a function of height above edge-on galaxies. And so one can see that decreases and actually may change, the dust type may change at about twiddle 5 kiloparsecs.
Great, thank you. Okay, so there's one thing I want to get to on the Slack. I see you all with your hands up. I will come back to you if there's time, but I do want to give some priority to the Slack, which I have strongly encouraged using. And so one, I think, very interesting comment that's gotten some discussion and replies is by Frank Vandenbosch. And he said, he loves your Wheel of Fortune, but he thinks the really hard question is how to heat cold gas. And in particular, how can we trust simulations if the dominant heating mechanism other than adiabatic compression is not treated properly? So if any of the panelists want to talk a little bit about heating, that would be, I think, useful.
So can I add something to that? More specifically, right? So there's cosmic ray heating, there's radiative heating, but often it's not included except for maybe a UV background. Drummond, you showed at some point this idea where you had this outflow and you had some cold gas in it. And then you showed that at the little, beyond 2 kiloparsec or something, you argue that some of that cold gas is being transferred back into the hot phase. Mm-hmm. And you link that to sort of a large scale turbulence of the hot material. And I'm trying to understand what you're trying to imply there. I have the impression that what you're trying to say is that, the large scale turbulence sort of stretches it out, it increases the area of the surface layer, and that will promote conduction. Because that's basically the only heating that's in that simulation, I suppose. So yeah, I'm wondering about the numerics and then whether we actually, are we fooling ourselves? Is this all numerical rather than physical?
Yeah. So, okay. So, we of course are doing all of this numerically, as you say, and you have a cold phase. It's got a contact discontinuity with a hot phase, and then you've got some turbulence, and that turbulence is going to mix up that contact discontinuity until the effective surface area gets so large that the conductive time, no matter what the actual conduction is, becomes fast, right? So this is, as Brent Tan put in his paper, this is why milk mixes into coffee, even though the molecular diffusion time is of order the age of the universe, but you stir it with the spoon and it builds up a surface area that's so large that you eventually mix and, as you say, heat the gas, conductively heat the gas. So, I think there is definitely a lot to be questioned about our simulations, and the fact that we're not resolving the field length, which is really what you would need to do to properly do this. I think both Brent and I have turbulent mixing layer simulations. Brent's are really nicely published in their recent turbulent combustion analogy paper, where they show that even resolving the field length, you get this mixing and this heating. And so the point I was trying to make about Evan's beautiful simulation with a turbulent background in the hot phase is it's doing exactly that. As you said, it's stretching out the clouds, it's splitting them into smaller and smaller parts until their surface area gets so large that in the case of her simulations, and I would say essentially 99% of our simulations, we reach the sort of the dissipative scale of our simulation, the grid scale, where they're numerically mixed. Even if we had infinite resolution, some small degree of thermal conduction, I think the same process would happen. That's my personal perspective. I think there's about 1,000 people in this chat who could add to that.
I think that's a great perspective. Okay, I'm going to go back to the hands. And I've seen Todd with his hand up for a while. So Todd, go ahead.
Thank you very much. And I really like the drift scan thing. And then I have a question related to that. So it's a sort of a two-part question. So the first part is that we use metals to try to get more information. There's just a lot of information there, but we have to have some kind of ionization correction oftentimes. So code like cloudy, which assumes thermal balance and ionization equilibrium, but the densities are expected to be low. So have folks looked at whether or not the timescales are indicating that that ionization code is even valid? Do we expect those equilibria? And then the second.
Uh-oh, Todd.
Yeah, I think we're losing you, Todd.
So anyway,
Todd is now frozen. So
all right, I think I got the gist of it. So let me try to start the answer to this, and I'd really encourage help from everyone. I think this relates back to a question Greg asked about Todd's discussion on Tuesday, where Todd showed some oxygen 6 absorption that was incredibly narrow, that pointed to very, very cold oxygen 6. And he hypothesized that this might be sort of over-ionized oxygen 6, something that oxygen 6 that has cooled so rapidly that its ionization hasn't been able to keep up. And I think that's a very compelling idea to explain those sorts of observations. Greg asked this question in particular, asking how common that is. And I don't think that question got picked up. So I'd like to just re-highlight it, because I'd love to know how common that is, because it bears on this question Todd asked now.
I think it's like 50% of the time, basically.
Wait, so I'm sorry, I actually lost my connection and missed the juicy answer I was looking for. But so as far as how common those narrow oxygen 6 absorbers are, we really don't know, because it's a super hard and expensive observation. I think I might have looked at the one quasar that's bright enough to do in an amount of time that a panel would go for. So that might be a question for future space telescopes, but I'm continuing to think about it.
Yeah, so I'll just very briefly say Suching Ji looked at turbulent radiative mixing layers like I look at with non-equilibrium cooling and ionization states. There, I think they didn't quite probe the rapid cooling enough regimes where you would get some of this out of equilibrium, over ionization of the oxygen-6. But I think it's the timescales aren't, especially for oxygen-6, aren't that different between ionization equilibrium and the cooling time. So I'm sure a bunch of people need to correct me on things I said wrong.
Thanks.
Okay, I'm going to go back to the hands, and I've seen Vijit. I'm sorry if I'm saying your name wrong, but I've seen your hand up for a while now. So if you want to go ahead and unmute.
Thanks. Awesome talk, Drummond. So my question is, it's rather a comment. So I really liked your Wheel of Fortune. So yeah, in the Wheel of Fortune, for all the different physical setups, you presented different criteria based on the cooling time and the flow time. To be very specific, the flow time. So can we generalize all these criteria based on the dump cooler number presented in Brent Tan's paper? As your simulations are nothing but hydro plus cooling setups, so the reaction time scale is nothing but the cooling time, and preferably it has to be the cooling time of the mixing phase, because that's the most relevant phase. And the flow time scale is nothing but it's the time scale for turbulence depending on the physical setup. And damp cooler number is nothing but the ratio of the reaction time scale to the flow time scale. So can we somehow generalize all this criteria based on the physics included in the setups? Let's say, in your case, cooling and the flow time scale. What do you think?
Yeah, I think you reiterated exactly the point I was trying to make. When I ended on the mixing time scale, that's really exactly the point. Yes, that if the cooling time is less than the mixing time, the eddy turnover time, or the ratio of the two, which is quite similar to the Dom color number, then I think this is a great way to look at it in general across all the different systems. It becomes a little, the reason why I wanted to put it the way I did is because when you're talking about, thermal instability in a stratified medium, it's not, Mark is making a point in the chats right now. Gravity changes things, buoyancy waves, gravity waves rather are different. So I tried to be a little more abstract, but I think you're hitting the nail on the head, really. I'd love to hear what Max or Brent has to say about this, or Prateek too.
Just one point. I just want to add one point. In that case, if there is gravity, or let's say there is magnetic field, or let's say there is thermal conduction or cosmic rays, I think the reaction time scale would change. It would just become a function of all the non-dimensional parameters which relate to those physical effects. For example, here the reaction time scale is T-cool mix, which depends on the cooling function at the intermediate temperature, to be precise. I think in that case that would be a function of all these parameters. Do you agree, Mark, with this point?
How about we hear from Max?
Yeah, I mean, I think, we will have a lot of interesting discussion about magnetic fields and so on in the non-thermal week. I'm pretty sure about that. So I don't know how much you want to get into this now, but I mean,
yeah, let's delay for non-thermal.
Let's delay it, all right. But I think your main point. Oh, sorry. Good.
Can I say
something? But your main point, I mean, was I agree with that, and it was along the lines also what Marcus mentioned earlier, right? His point, I think they're just great analogies. So I think kind of sums it up.
I may say one sentence. Since there was a question directed at me, right? Yeah, the reason gravity is different is because it makes what's going on depend on the macroscopic environment. And so when a medium is stratified, then what's happening depends on larger scale conditions, okay? And that's different from all the different other things that can happen on the micro scale.
So I also want to respond. See, T-mix is something which is, we cannot get it a priori, right? It's good to think in terms of, it's a good physical quantity, but it's an incredibly difficult quantity to measure because it depends on how mixing is driven. Is it through thermal instability or, penetrating filaments? So we need something which is more measurable and more physical. And eventually, of course, it leads to turbulence and mixing. But, we have to sort of distinguish the physics of it and, and how it is actually driven given a setup.
Mm-hmm. Thank you.
Well said, Prateek. Thank you. Okay, so I have seen Joe Hanawi with his hand patiently raised for the last 20 minutes or so. Go ahead, Joe.
Yeah, thanks. Hi, Joe Hanawi, everybody. UC Santa Barbara. So Drummond, first of all, amazing talk. I think it's cool that Chris is here because obviously there's a clear arrow of progress from Klein, McKee et al. 1994, where these sorts of first idealized calculations of cloud crushing, et cetera, were being done. My question is how, for the entire panel, is how do we build a bridge from all of these idealized simulations where we're actually really resolving the physics and learning a lot about the physical processes, whether that be crushing or condensation, et cetera, growing small scale structure or dissipating small scale structure, and like the cosmological simulations that come nowhere near resolving that structure. In other words, if somebody claims that they get the covering factor of silicon-2 absorbers right in such and such cosmological simulation, so should I believe that? Should I not believe that? How do we build that bridge?
Maybe I'll start. So, to my mind, there's two directions. One is, people are throwing more and more resolution out in the CGM, right? In these cosmological simulations, look at Dylan Nelson and the rest of the TNG50s group, look at, Tempest and Foggy and Freke van der Voort simulations. And so there's lots of stuff out there. And I think there's a lot to be done with very careful analysis of those simulations to see if the processes we're seeing in the idealized setups translate and are at play in those simulations. I think Dylan and Prateek just did a nice look at this of the cold clouds in the CGM of LRG galaxies. So that's sort of one direction to go, is to try to push the CGM to higher and higher resolution in cosmological simulations and make a connection there. And then I guess I'll echo Cameron Hummels' point from the chat, and he says, answer, subgrid models. So Cameron has been a big proponent, as have many of us, about actually coming up with a subgrid model for the sort of unresolvable or incredibly difficult to resolve cold phase in the CGM. And so maybe that's what we need to do, is just say, punt, we can't get the hydrodynamics right while still getting the global dynamics right. So let's move it all to a subgrid model. I think Neil Katz and his student, who I'm embarrassingly blanking on, just put out I think one of the first attempts to start to do this. And there's many of us working on this now. So I would say those are the two pathways forward that I see. And I think, because I think you've really addressed a key question for the theorists, is we have to bridge these two worlds.
Just one small follow-up, which is, so what is the minimal resolution, I guess? This is the thing I'm trying to understand, is how far away are we from this? I'm not discounting that the cosmological simulations that load all of this resolution into the CGM, I think those are incredibly important, but just how close are we?
Evan?
If I may.
Yeah,
I want Evan to talk. Okay.
Okay, I think this is directly related to the point that I brought up earlier about which size scale we care about. So I think that if the CGM is truly a mist, right, there aren't big clouds, everything is in tiny droplets, then there's no getting around it. We have to have a subgrid model, right? But if the CGM is actually composed of much larger scale structures, and they have some small droplets, within them or surrounding them, but that's not what's determining the bulk dynamics or say the covering fractions, then maybe we're almost, I mean, maybe TMG50 is there, right? So I think that is a really important question, because I think that it's essentially, which size scale do you care about? Do you care about the smallest sizes, or do you care about the bulk structures? And I think that, if it's the bulk structures, then in some sense this is going to be easier. But I don't think that we know at all. And that's why I made the point that I think it's really interesting that so far from the theory side, I've not seen evidence that we should believe that it's the tiniest scale that matters, at least for, understanding the properties of the CGM.
Oh, well, I think I just showed 3 plots that show that we do need to resolve CST cool if you want to get the phase structure correct. If you want, I mean, there's been all these questions about pressure equilibrium. And so if you want to make a detailed observational prediction, you need to get the phase structure right. If you want to get the total amount of cold gas below 20,000 Kelvin, that might be easier. I know Max is.
So I will not retract, but weaken my statement by saying 100% the answer depends on the question you are trying to answer.
Yeah, if I may.
Please.
I just want to also dwell on that point that if you want to compare to observations, I mean, I'm interested in Lyman author radiative transfer or Lyman continuum escape, for instance. I think these small structures are very important, right? So if you're interested in just the total cold gas content, I think Freke van der Voort gave a very nice talk here at KITP during this multiphase workshop to show, that even in this enhanced resolution simulations, they are not converged yet on this cold gas structure. And from the theory side, I would say, we know that at least we don't have to resolve the field length in order to get this m dot right. But to just make one extra point on, that it's not just the size of this cold gas structures. I mean, in these turbulent boxes Drummond was showing, I think what is also important, is where basically your turbulence falls off because of your numerics, right? And that's not the cell width, that's in fact, many times the cell size, right? So I'm actually quite worried about, in simulations we are also running that, if you maybe keep small cold gas structures artificially because of this effect, because your dissipation, the numerical dissipation scale there is much larger than your cell width. So that's something to care about. So to just answer your question, Joe, I think, like cosmological simulations not resolved in this total cold gas mass as Freke showed, not even sure if our simplified turbulent boxes are resolved, but let's see with that. But sure about the turbulent mixing layers. Sorry.
I just want to point out there's a lot of really good stuff happening in the Slack, but there's some interesting stuff happening in the Zoom chat too. The people who are typing these very substantive, remarks in the Zoom chat, I encourage you, Joel Bregman especially, Claude Andre, Martin, go head over and put these in the Slack. That's where these comments are going to be preserved and commented on asynchronously by everybody who's available at the talk today. We don't have infinite time. Go over to the Slack. One more announcement. Drummond referred to an after party in the hotel lobby, just kidding. The after party, if you want to know the details, I guess, head over to Halo 21 Precipitation channel on Slack, where the details have been posted. That's a half hour. We have 4 more minutes. 2 people have been sitting here with their hands raised for patient, 30 minutes or so. Rangman, Kartik, I'll take your questions, and then we're going to conclude our plenary discussion and thank everybody again. But Rangman, go ahead.
Thanks, Jess. I just wanted to push back on your comment, actually, on the Slack, that we have somehow observations are lagging behind theory, right? I just want to push back. It's maybe my observer bias, but I just want to point out that we have a fantastic laboratory right next to us, the Milky Way, which is amazing for small scale distribution of gas. For example, the Fermi bubble, perfect example of multiphase outflow, where we have hot gas. We have hundreds of cool resolved clumps seen by this incredible paper by Enrico Di Toledo and collaborators of 21 centimeter cool gas, which also exists in molecular gas, which kind of goes away after a few kiloparsecs. Then we have the UV absorption we see in train gas. So there is a fantastic reservoir of observation that exists, which I hope the theorists will look into to compare their predictions, how it tallies up. Like Drummond's beautiful simulations, the beautiful the 2D laminar flows. Do you actually can make predictions like we see in the Fermi bubble? Might be a great place to compare and try to constrain them, perhaps.
All right, thank you, Rongma. I think you just volunteered yourself to sit on a panel during Milky Way week. And of course, most people here know I agree with you about the Milky Way being the best galaxy. There is a Halo 21 Milky Way channel, by the way, where I think a lot of the future of the CDM progress, observational progress is going to happen. Head over to that channel if you're interested. Milky Way week is week 4. Don't forget. Okay, Kartik.
Hi. So I was wondering, Drummond, you talked about all this importance of cooling in the mixing layer. I mean, the radiation that has been cooled, you were assuming we all take when we do hydrodynamic simulations that they just leave the system. So I was wondering how much radiation does it get out of this box? I mean, how much radiation does one system go out? Can it be a significant source of ionizing radiation in the CGM or in the IGM? So how much of it is coming out? That's the basic question. What fraction of the kinetic energy is radiated as UV radiation?
Boy, this is like a qualifying exam right now. I'm trying to do the math in my head really quickly. I think this is a really interesting comment. In particular, when I hear that, I think, okay, so we have option 6. It's emitting really short wavelength photons, and that could then ionize nearby, neutral hydrogen or something like that. And I remember I had a conversation when I was visiting you guys at IISc with Biman Nath about this exact question. This was now 4 years ago, and I still don't have a good answer. So I'd love to hear if anyone else here has a good answer. Maybe we can follow up with this over. We should start a Slack thread on this so we can.
Yeah. That's exactly what I was going to say. Kartik, would you mind starting a Slack thread on this exact question so that people have time to comment asynchronously? Peng, I see your hand, and it pains me to tell you to please, I'm going to have to defer to the Slack. It is now 9:59 a.m. Pacific time. We are all at the same time inspired but exhausted by this incredibly rich discussion. Let's thank Drummond and all of our panelists again. Thank you so much. Today was really great. And of course, we will have time tomorrow for more discussion during our Structured Friday discussions. Please come back. I know it's going to be very exciting. I will be looking at the Multiphase channel. We'll be voting on the questions that we talk about. So thanks, everybody. We'll see you back here tomorrow, bright and early. Have a great day.
Thank you, Jess.
Thanks, everybody.
Bye.
Really good.